Okay, so I mentioned in the number 7 challenge that I would not be doing like an improvement to the code, but I figured I actually wanted to see what sort of improvement I'd get speed wise. So yeah, that's what this video is going to be. It's going to be like 7.1. I'm going to try and include the square root thing that I was talking about. Go watch the previous video if you have no idea what I'm talking about. So yeah, that's what this video is going to be. Let's get going. So what I'm going to need, I think, is I'm going to need a new list that's going to be the primes that we're going to check. So where I'm calling the list of primes here, this is now going to be like list of primes to check. So the only ones that we need to check. So we need to initialize that list. Set that equal to empty list. Now, when we append our prime to our list, what we need to do is keep track of what prime this is. Keep track of like the number prime it is, so like its index, and keep track of whether or not that specific one is currently in our range. Because we're iterating up, we're going up from 2, then 3, then 4, and so on. We're never going to be, once we add a list, once we add a number to our list of primes to check. So once say we know 2 is a number we need to check, if it's divisible by it, we're never going to take that out because we're only increasing our x. Our x never goes down. This probably doesn't make a lot of sense, but hopefully it will when it's done. I'll try and go back over it once it's done. But yeah, so because of that, we can try and keep track of like an index. So I'm going to just initialize index and say it's 0. Now I'm going to say down here, I'm going to say if list of primes index, so list of primes 0 is less than the square root. What was the square root of? So the square root of the prime, or the square root of x. Square root of x, isn't it? So less than x to the power 0.5. Then we want to add this prime to our primes to check. So list of primes to check dot append list of primes index. I think that's right. We're probably going to get an error here because what I'm thinking is once we've done that, we now need to do index plus equals 1, and by doing that, our index is sometimes going to be out of range for the list of primes. I think we're going to get an error. We might not, but I think we will, and I'll have to figure that problem out in a sec. So let me just see what this does for now. I'm going to find the 100th prime number, and I'm going to print out. What am I going to print? I'm going to print out right here the list of primes and the list of primes to check, as well as our x value. I'm going to drop this number to 10 so that we don't get a spam print. So 007.1. So we didn't actually get an error. This actually seems to be working as intended. So the first time we add to our list of primes is when we get up to index 5. Index 5 obviously is now above, but I'm thinking is, yeah, hold on. So our list of primes is obviously wrong because this 4 shouldn't be in there. So I'm thinking the reason that is because 2 wasn't put into our list of primes to check until after 5. So you see now 6 isn't in there because 6 is divisible by 2. So it hasn't made the error there. So the first number is going to be wrong. What I need to do is, if it's less than this plus 1, I think we'll fix. So if I save that, 4. Yeah, so you see now 4's gone. So what this was doing was it was rounding down. So if I said x times by, sorry, x to the power 0.5, it was it rounding? So when x was 4, when x was 4, the list of primes to check was probably still empty. Well, in fact, we know it was empty because we printed it out up here whenever we added to it. So yeah, we know it was empty. Obviously, we don't want that. We want it to be added. Now, 2 was only added to the list of primes to check once we got to 5. We got to 5, realised 5. That's why, because this is strictly less than. This is strictly less than, so when this returned, when this x was 4, and we said 4 to the power of 0.5, which is 2, we said if 2 is less than 2, which it's not, 2 is actually equal to 2. So yeah, we just need to add like a 1 to this. It doesn't have to be 1, it could be like 0.1 or whatever, but I'm just going to keep it at 1. And this will now work. So hopefully this gives us a speed increase. I'm not sure if it will because of the square rooting right here. I'm not sure how computationally intensive that is, but I guess we'll see now when I comment out this. Make this 10,001, save and run. So we get 0.1 seconds to do it. Now I'm pretty sure didn't it take us like 6 seconds before to do it? Yeah, there we go. So we've dropped our computation time down by like what, like a tenth, less than a tenth. It's like a 60th of the time. So yeah, just adding this one change, adding in like a list of primes to check, and then hopefully this makes sense. I haven't actually explained this very well at all, but yeah, if you want to improve on the solution to 7, then this is probably the way to do it. So now I can do things like 100,001, and you can see we can do this in probably less than the 6 seconds. Yep, so 3.5 seconds. So now we've found the first 100,000 primes in just over 3.5 seconds. Every single prime number will be there. So if I print out list of primes, this is going to take a while because of the print. It takes a while to print stuff to a console. But yeah, you can see here we've got all the prime numbers up to the 100,000th one, and it hasn't actually taken as long as I thought it would do. 3.5 seconds to print out first 100,000. So if I print out like the first 1,000,000 primes, I reckon this is going to take probably 20 seconds, maybe longer. Yeah, probably will take longer. It'll probably take 40 seconds, I think. We'll see. I'll leave that running while I try and explain this a little bit better. So what we're doing here is we're checking. So where we were checking if each number was prime against the list of primes we already had. Now we're only checking against the primes we need to check. Now, list of primes to check, the idea is that this will get populated with all the primes that are less than the square root of the number we're checking, so x in this case. Now, to create this list, what we do is once we find a number that is prime, we say, is this number, once we find a number that is prime, we append it to our list of primes, because this is going to be all of our prime numbers, this list of primes. Now we say if the list of primes at index, so index is going to be 0 to start with, so if the first prime we find is less than the square root of x plus 1, then we're going to append it to our list of primes to check, because we know that first prime now is less than x and less than the square root of x, and we therefore need to be checking this number. You can see this has just ended 80 seconds it took, so twice as long as I thought it would take. But still, it's really quick considering we're doing like 1,000,000 primes there. Anyway, back to this. So once we append this number from list of primes into list of primes to check, because we now know it needs to be checked because it's less than the square root of x. We now know that index can be iterated, so we're now going to be checking the next element, because if you look at the if I print out the first 10 primes, so you can see these are all in ascending order, so it's going to check 2, and it's going to, for when x is 1, it's going to say, right, 1 is not, the square root of 1 plus 1 is not less than 2, actually equal to 2, therefore we don't need to append, sorry, it's never going to be 1 because x is starting at 2. Okay, so for 2, it's going to append that to our list straight away. Now for 3, it's not going to append it straight away. It's going to come in with 3 and say, right, the square root of 3 is like 1.5, 1.67 or so, 1.7, something like that. 1.6 and 7, somewhere between that. So it's going to say the square root of 3 plus 1 is not less than 3. Which is our first index. Remember, it's 0 indexing. Therefore, we don't need to append it to this, and we don't iterate the index. So we just skip this, start again, but with a new x this time because x is being iterated. And now we do the same thing again with the same index. So we check 3 repeatedly over and over until it is less than the number we need it to be, which is the square root of x. Then when we've added it, we iterate our index, which means we're now checking 5. We're not checking 4 because 4 isn't actually in here. Our index gets iterated, which means it's the next number in the list. Hopefully that makes sense. I've probably messed this up completely trying to explain it, but yeah. If you want to see the improvement, here it is. People might find this interesting. I quite like seeing the computational time difference between like doing the brute force way and a slightly cleverer way. So yeah, here it is. Enjoy. If you like the video, like it. If you want to see more, subscribe. You know what to do. I'll see you in the next video. Thanks for watching.